Hello everyone, today I will be presenting you the work that Alvaro Lorca and I have been doing on data-driven optimization for transmission and storage capacity expansion under seismic risk. The presentation is divided in 6 sections. I will begin with a brief introduction, then I will review our seismic uncertainty modeling approach. In the third section, I will cover the developed optimization models of our framework. Immediately after that, I will present you the solution method. Finally, I will show a case study and make concluding remarks. Let's go with introduction. Electricity supply plays an essential role in our society, so evaluating and planning for power networks' safe and reliable operation is paramount. As the figure shows, power systems are divided into some sectors, such as power generation and transmission networks. In this work, we will be putting the focus on those. Many possible disruptions threaten electric power networks, and this is a big concern for planners. Among those disruptions, we notice that earthquakes can severely damage those systems in seismic regions of our planet, so this hazard is essential to be taken into account. Having this motivation in mind, we proposed a novel framework based on data-driven optimization for transmission and storage capacity expansion under seismic risk. Our framework is divided into 3 parts. First, we have the seismic uncertainty modeling. The second part takes the results of the seismic models to develop optimization models. The last part covers the solution method required for the optimization models. The main contributions of this work are summarized in the following 3 points. First, we propose a novel earthquake attacker defender model capable of spotting realistic worst-case earthquake scenarios. Second, we develop a new approach for seismic resilient planning using a data-driven stochastic robust scheme that leverages distributional information of multiple seismic sources. Third, we present experimental evidence that confirms the efficiency and the effectiveness of our framework. Now I will continue with a short explanation for the seismic uncertainty modeling. There are 2 types of uncertainties related to earthquakes: the risk of ground motions and their impacts on the electric power network's components. To model these uncertainties, we simulate scenarios to represent the nature of the hazard. The procedure to simulate those scenarios is divided into 3 steps. First, we generate peak bound acceleration vectors, or PGAs, sample weights, and labels that indicate which source produces the motion. Then, we evaluate the functionality of components for all the scenarios and recovery stages of interest using a function based on fragility and recovery curves. Finally, we stack the scenarios of functionality along with sample weights and labels. We have to do the observation that, in this work, we consider that earthquakes only damage substations. The following part of our framework corresponds to the optimization models. I will begin this section by presenting our operational model. Then, based on the previous model, I will explain our earthquake attacker defender model, which spots worst-case contingencies. Finally, I will review our data-driven stochastic robust optimization planning model. To represent the system's behavior after an earthquake, we consider an operation horizon, divided into recovery stages, where each stage is described by representative days. Then, our operational model is a linear minimization problem that finds the optimal economical operation of energy storage systems and power units, satisfying engineering and physical constraints. The constraints involve limits of generation, energy not supplied, and line flows. Also, we consider the voltage relation of neighbor buses, allowable voltage angles, load balance, and constraints regarding storage systems. Given the operational model, we can develop the earthquake attacker defender model. This model finds worst-case contingencies that maximize the operational cost of the network, satisfying structural limits and data-driven constraints. In our model, contingencies psi are found within what is called an uncertainty set. This set is defined as the intersection of a structural constraints set and a data-driven set. The structural constraints set considers limits in substations functionality due rate, transmission lines capacity due rate, and constraints that allow the total disconnection of transmission lines given some damage threshold. Further, we propose a novel uncertainty set of adjustable sizes based on data samples of uncertain parameters. This set allows us to incorporate information of earthquake scenarios to find realistic worst-case contingencies. The procedure to define this set involves several steps with various calculations. For the sake of simplicity, I will give a graphical explanation of our set. We define a polyhedron on a reduced dimension based on a large number of data samples using principal component analysis and a clustering technique. Then we find in this polyhedron a vector omega, which, when projected to the original space of data samples, namely vector phi, results in the maximization of the system's operational cost. In addition, we can easily adjust the size of the data-driven set according to the percentage of sample weights included in it, following some arithmetic operations. After the definition of the earthquake attacker defender, we can define our data-driven stochastic robust power network planning model. This model has two main characteristics. It incorporates distributional information about multiple seismic sources and captures complex uncertainty data structures employing our uncertainty sets. The compact formulation is as presented. The outer level of the problem decides investments in transmission lines capacity expansions and siting and sizing of energy storage systems to minimize the expected cost of the inner earthquake attacker defender problem's worst case operational cost among seismic sources. Due to their multi-level structures, commercial solvers cannot solve both the earthquake attacker defender model and the data-driven stochastic robust models. Thus, we must find suitable solution techniques to handle them. Two algorithms constitute our solution method. The scheme shows the alternating direction method on the left, which is used to solve the earthquake attacker defender model. First, we initialize the algorithm defining a vector of damage. Then, we solve the dualized operational problem with the fixed damage. After that, we solve the attacker level problem with the fixed dual operational variables. Further, we check if the convergence criterion is met. The algorithm ends if it converges or continues iterating otherwise. On the right, we present the column and constraint generation method. This method is used for solving the data-driven stochastic robust planning model. The first step is to initialize a master problem, a linear relaxation of the full model. The next step is to solve the model. Further, the algorithm initializes and solves the subproblems for each seismic source. After that, the convergence criterion is checked to evaluate if the algorithm continues or stops. Having presented the models and the solution method, we can continue with a case study, for which we have chosen the Chilean electric power system. For the experiments, we use 281 node Chilean power network description and 20,000 simulations of seismic scenarios, considering moment magnitudes equal or higher than 5. Concerning the computation, we implemented the optimization models in Julia 1.5 in the jump environment using Gurobi version 9. We solved the models and algorithms with a Dell PowerEdge R360 server with a processor running at 2.2 GHz with 64 GB of RAM. Here I present an example of the solutions obtained from the Earthquake Attacker Defender model. The figures show the functionality rate of components 3 days after the occurrence of an earthquake in the colored seismic source. The model is tested for two different sizes of the uncertainty set, one that considers 95% of the data samples included, and the other with 99% of the samples included. The system presents more damage when the set is enlarged, an expectable result. Note that these maps help us visualize worst-case damage scenarios caused by earthquakes. We also run some experiments with our investment model. We tested the results of 50 and $100 million budgets for different levels of risk. We found that when compared with a network without investment, the energy not supplied was reduced significantly, ranging from 2% to 10% of reductions. The improvement of performance under earthquakes shows significant opportunities for seismic resilient planning in the Chilean system. Further, we present a closer look at an investment solution. It is clear that the whole budget is invested in the country's northern region, and the investment is diversified, so there is no single critical investment that takes the budget's totality. Also, we see that the model prefers investments in transmission lines rather than in storage systems. This is seen too in other investment configurations. Now, I will make some concluding remarks. In this work, we have developed a comprehensive framework that decision makers can use to assess the seismic resilience of power networks and plan investments to improve their performance after earthquakes. We have also provided some experimental results that show the effectiveness of our framework and confirm its value for seismic resilient planning decisions. Well, this is our proposal of data-driven optimization for transmission and storage capacity expansion under seismic risk. Thank you for your time.